As usual, it's very instructive to take a look at the simplest brute force algorithm for the problem. We'll look at that in a little detail because it illustrates really what the fundamental issues involved with getting efficient algorithms for this. And it's also the basis for more efficient algorithms. So the brute force method we could give in a beginning programming class. You have your text. You have an index I that indexes into the text. And you have an index j that indexes into the pattern. And start out with both I and j at 0, and you compare text to pattern, and you keep going until you find a mismatch. If you find a mismatch before the end of the pattern, then what you do is move the pattern over one position. That corresponds to simply incrementing the text pointer. And then here we have a mismatch right away, so we move the pattern over one position, increment the text pointer. And then starting with I at 2, we compare the second text character with j at 0, the first pattern character. Increment j to 1, increment I to 3, we have a mismatch. Mismatch happens at j and I plus j. The jth character of the pattern versus the I plus jth character of the text. Now we have a mismatch, move over, that's increment I to 3, compare the first character of the pattern, j equals 0, with the I plus jth pattern of the text. That's a mismatch, move over one. So we go, first one is a match, the second one, j is 1, I is 4, compare against 5, that's a mismatch. Move the pattern over one, it's a mismatch. Finally we get to I equals position 6, and we go for j equals 0, 1, 2, 3, all matches. When j gets to 4, which is the number of characters in the pattern, that's when we know we found a match. So in this table, the entries in gray are just there for reference. The black ones are when we found matches, and the red ones are where we found mismatches. So we do the trace before the code because the code is extremely simple. So this is to implement brute force substring search to look for a pattern, a given pattern in a given text. Or for Java's index of, this would be the index of method in string that takes the argument pattern. So we get the pattern length, we get the text length. And we're going to potentially look at every, the pattern could start at any position in the text from 0 to n minus n. And for every value of I, we create a new j, and we look for the match between the pattern at position j and the text character at position I plus j. If we get all the way to j equals m, then we found a match at I. If we get a mismatch, then we get a break before j equals m, and we go and try the next value of I. And if we get all the way through there without returning, then we just return n, which is 1 past the index of the last text character, the length of the text, and that's an indication that the pattern was not found in the text. Very straightforward implementation of the pattern match algorithm. Now, the key point is that this algorithm is fine in many contexts, and actually it's the one that Java's index of uses. But the real problem is that it can be slow. Number one, just the algorithmic problem, it can be slow if there's a lot of repeat or repetitive characters in the text and the pattern. For example, suppose that the text is all A's and a B, and imagine that there's a billion A's and a B or whatever. And then the pattern also is a smaller copy of the same thing, all A's and a B. Then what happens in this case is that for every possible position matching the pattern against the text, we go through all the pattern characters and we only find the mismatch on the last one. So, and then we find the mismatch, we have to go over one, try them all, find the mismatch in the last one. And we eventually do find a match. But for every text character, we've looked at almost m-1 pattern characters. So this is the worst case that shows that the running time of the brute force algorithm can be proportional to m times n, where m is the pattern length. And the pattern could be long, say the pattern could be 100 characters, and n could be huge, like a billion, and that's going to be slow, particularly by comparison with the alternatives that we're going to look at. Now, a more important issue than just the worst case performance is the idea of backup. As I mentioned, for lots of applications, if we're going to put our machine on one of the wires of the internet and watching this input go by, or if we just take the abstract standard input model, you don't get to back up when you find a mismatch. But the brute force algorithm is always backing up. If we go through matching our pattern against our text, when we find a mismatch, we say we want to move the potential pattern over one position, but that means backing up in the text. So we would, there's ways to deal with that by saving the most recent m text characters that we've seen, but it's definitely problematic for larger patterns and certainly inconvenient. So the brute force algorithm uses backup. And so you could maintain a buffer, as I mentioned, but what we're going to look at is an ingenious way, a couple of ingenious ways to avoid having to do backup. To set up for that, we're going to look at a slightly different implementation or alternate implementation of brute force. It compares the same characters as the previous implementation, but it does things in a slightly different order without a second for loop, and it does the explicit backup. So let's look at that. So we have our I and j pointers, and we initialize them both at 0. And so it's a for loop where I gets incremented on every iteration through the loop. And so what we do is, as long as we see a match, we also increment j. So that while the pattern is matching, we're incrementing both I and j. When we see a mismatch, what we do is just subtract the current value of j from the I pointer. That's the next character that we have to look at. When we find this mismatch, we want to subtract the current value of j, then increment I at the end of the for loop, and that puts us right on the next text character that we want to look at, and then we reset j to 0. So this is does the same character comparisons, but it explicitly shows that we're backing up in the text. And then if we ever get to the end of the pattern, then we return I minus m, which is the position of the first character in the text that matches the pattern, which we found there was m matches. So that's an alternate implementation that we'll come back to. So the idea is that there's a couple of algorithm challenges. Even though this brute force method is simple, it's not always good enough. And so the first one is just from a purely algorithmic standpoint, this is a challenge. Do we need n times m, where m is the length of the pattern, or can we do it in time independent of the length of the pattern? What we want is a linear time guarantee, and that was a fundamental algorithmic problem that people worried about for a bit, and we're going to look at how people approach this fundamental algorithmic problem. And then there's the practical challenge of we might not have the room or the time to save the text, and actually the judge might not be happy about us saving text away in some computer. So we want to avoid backup in the text stream. All we're supposed to know about is our pattern, and we're supposed to light the light if we find our pattern, and that's it. So what we're going to see next is a way to deal with both of those challenges at the same time.